Welcome back to the Deep Dive. We're here to give you those essential shortcuts into the big technical reports shaping AI.
And today, we've got a really interesting one.
Yeah, we're diving into the Kimi K2 technical report. And it's not just another L on paper, is it? It feels like something bigger.
Oh, definitely. It details this pretty massive shift. We're moving from models that just process information towards what they call agentic intelligence.
Agentic intelligence. Okay, break that down.
It basically means models that can, perceive their environment, plan things out over multiple steps, actually use tools, and then act autonomously.
So less like a talking encyclopedia, more like a digital assistant that can actually do stuff.
Exactly, that's the goal. So our mission today is to dig into how the Kimi team built K2 to make that happen.
Right, and the scale is kind of mind-blowing, 1.04 trillion parameters. But it's a mixture of experts, a MOE model.
Yep. We need to get into that architecture, the training, and how it stacks up performance-wise, especially because it's open source.
Okay, so let's start with the core problem they were tackling. Why build this agentic model in the first place?
Well, the issue is the data. If you want a model that can, say, book your flights or debug code, you need training data showing that kind of multi-step reasoning and tool use.
And that kind of data is hard to come by.
Incredibly rare in just, scraping the web or books. Human language doesn't often detail every single step of complex actions perfectly, and scaling that kind of data generation is super costly.
So it's not just about making the model bigger, you need smarter training. Which brings us to this idea of token efficiency.
Precisely. Token efficiency is all about how much useful learning signal the model gets from each piece of data, each token.
Because the really good agentic data is scarce and expensive.
Right. So the challenge is sort of twofold. First, how do you build a truly massive model like Kimi K2 stable enough to train on huge general data sets? And second, how do you make absolutely sure that the precious agentic data you do have gives you the biggest possible learning boost?
Which leads us to the architecture. Mixture of experts, MOE. We hear this term a lot. How should we think about it for a model this size?
Okay, imagine instead of one giant brain, you have a huge committee, like 384 specialists. That's the 1.04 trillion parameters total capacity.
Okay, big committee.
But crucially, when you ask it something, it doesn't consult everyone. It intelligently picks just a few, in K2's case, only 8 experts, which corresponds to about 32 billion active parameters at any one time.
So it routes the query to the right specialists for that specific task.
Exactly. Makes it way more compute efficient than activating the whole trillion parameters every single time.
That makes sense. And that ties into their first big innovation, right? Dealing with the stability of training such a massive MOE, they use something called the muon clip optimizer.
Yeah, this is some really clever engineering. See, older efficient optimizers, like the original Muon, they had this big problem with training instability.
Right.
Models would just crash.
Crash out. What goes wrong?
It often came down to something called exploding attention logits. Sounds dramatic, I know.
It does. Give me the simple version. What's an exploding logit?
Think of the attention mechanism inside the model constantly comparing things. Like, is this piece of information, the key, relevant to what I'm looking for, the query? The logit is the internal score of that comparison.
Okay.
If those scores get way too high, like feedback loop high, the numbers just become too big for the computer. It causes an overflow, the math breaks down, and boom, lost spike. Your training run is ruined, weeks of work gone.
Yikes. Okay, so stability is absolutely critical. How does MuonClip prevent that?
It introduces this neat trick called QK clip, query key clip. Think of it like an automatic volume control. It constantly checks the maximum attention score being generated.
Right.
If that score starts getting dangerously high, QK clip automatically subtly adjusts the internal query and key values to bring it back into a safe range. It's like a pressure release valve for the math.
And the proof is in the pudding, I guess. They trained Kimi K2 on how many tokens?
An insane amount. 15.5 trillion tokens. And the paper reports they did it with 0 lost spikes.
0. On 15.5 trillion tokens.
0. It's a huge validation. It basically says, okay, we've cracked the stability problem for these giant, efficient MOE models using this QK clip technique.
That's a massive engineering win. It unlocks the efficiency without the risk.
It really is foundational. Allows them to get the benefits without the constant fear of the training run collapsing.
Okay, so stability handled. Let's pivot back to the data problem. The lack of good agentic data. If you can't find enough real-world examples of complex tool use, how did they teach K2?
They basically decided to make their own. Large-scale agentic data synthesis.
Synthesizing agent data. How does that work?
They built a pipeline that generates these complex, multi-step tool use demonstrations. And the key is, these aren't just made-up stories. They're often executed in simulated environments or even real ones, like coding sandboxes.
Ah, so they're verifiably correct. The actions described actually achieve the goal in the simulation.
Precisely. That ensures the data is grounded, high fidelity, and actually teaches the model how to use tools correctly across different scenarios.
That's clever. Solving data scarcity by generating verified synthetic data. Okay, let's dig back into the architecture, that sparsity. 384 experts total, but only 8 active. You mentioned a sparsity scaling law.
Yeah, this was a really interesting finding they highlighted. They discovered something sort of counterintuitive. If you keep the amount of computation fixed, meaning the number of active experts and parameters stays the same, like those 8 experts, 32 billion params.
Okay, fixed compute budget.
Increasing the total number of experts available in the pool, going from, say, 128 total experts to 384, actually improves the model's performance significantly.
Wait, hold on. If you're still only using 8 experts, why does having a bigger pool to choose from make the model smarter? Isn't that just wasted parameters sitting there?
It's not waste, it's about specialization and choice. Think about it like this. If you only have 128 experts in your library, each one has to cover a broader range of topics. Your science expert might cover physics and biology and chemistry. But if you have 384 experts, you can have one just for quantum physics, another for organic chemistry, another for molecular biology. So even though the model only activates 8 pages from the library for any given query,
The chance that those 8 pages are exactly the right super specialized ones is much higher because the library itself is bigger and more diverse.
you got it. It improves the quality of the selection, even with the same compute cost per token. More choice leads to better specialization.
That makes a lot of sense. Maximizing the utility of the routing choice. Okay, and before they get to the final RL tuning, they also did something with the general data using rephrasing to boost token utility.
Yeah, another smart technique. The idea is simple. How do you get the most learning out of every token, especially for valuable knowledge or math data? Just repeating the same data over and over, like doing 10 epochs, often leads to overfitting. The model just memorizes the exact phrasing.
Right, it learns the surface form, not the underlying concept.
Exactly. So instead, they used other LLMs to automatically rephrase the original knowledge and math data. They generate multiple versions, different wording, different angles, different styles, all conveying the same core information.
And training on this rephrased data was better than just repeating the original.
Significantly better. They found, for instance, that training once on a dataset where each fact was rephrased 10 times actually beat training 10 times, 10 epochs, on the original raw data. On benchmarks like Simple QA, this rephrasing gave a big accuracy boost.
Wow. So it forces the model to generalize the concept because it sees it expressed in so many different ways.
That's the idea. Teaches the concepts, not just the specific words. It's a powerful way to make limited, high-quality data go further.
Okay, fascinating stuff on the data side. Now, the final stages, post-training. This involved supervised fine-tuning, SFT, on that synthetic agentic data, and then reinforcement learning, RL.
Right. And the RL part is particularly sophisticated because they needed the agent to learn in very different kinds of environments. So they used a hybrid approach, 2 main reward systems.
What's the first one?
That's a verifiable rewards gym. This is for tasks where there's a clear right or wrong answer.
Like coding or math problems.
Exactly. Did the code pass the tests? Did the math proof verify? The reward is deterministic, objective, pass-fail. Simple.
Okay, that covers the objective stuff. But what about fuzzier tasks? Creative writing, open-ended questions, strategy discussions. There's no single right answer there.
And that's where the second mechanism, the self-critique rubric reward, comes in. This is really interesting.
Self-critique. How does the model judge itself reliably? Doesn't it just give itself an A+ space?
No, that's the clever part. It doesn't judge in a vacuum. It evaluates its own output, yes, but it does so by comparing it against a predefined set of external rubrics.
Rubrics, like grading criteria.
Exactly. These rubrics are carefully curated to define what good looks like for that subjective task. Things like helpfulness, coherence, following instructions, adhering to safety guidelines. The model generates an output, then critiques it based on the rubric, maybe tries again to improve its score against that rubric.
Ah, so the rubrics provide the objective grounding, even for sective tasks.
Yeah.
The model learns to align its outputs with those external standards.
Precisely. It's teaching alignment not just on static examples, but as a dynamic process of self-improvement against defined principles, even in open-ended domains.
That sounds like a really powerful approach to alignment. Okay, methodology laid out. Let's get to the results. How did Kimi K2 actually perform on these agentic benchmarks? Did the approach work?
Oh yeah, it worked. Kimi Puntu basically set a new standard for open source models in these areas. On Tao2 Bench, which is a tough multi-turn tool use benchmark, it hit 66.1. On AC Bench, another agent benchmark, 76.5.
Pretty strong numbers. What about something really practical like software engineering? That seems like a key agentic skill.
That's one of the headline results. On SWE Bench, verified this involves fixing real bugs from GitHub repositories. K2 scored 65.8% on its first try.
65.8% on real bug fixing. How does that compare?
It significantly closes the gap with some of the top closed source models out there, like Claude 4 Opus or Sonnet. It shows open source is really catching up fast in these complex interactive tasks.
That's huge. And was it just good at agentic stuff, or did the underlying reasoning and coding skills hold up generally?
They held up really well. It wasn't a one-trick pony. It actually leads among open source models on general coding benchmarks like Live Code Bench v6, getting 53.7%. And on GPQA Diamond, which tests deep reasoning, it got 75.1%.
So it's strong across the board, but particularly state-of-the-art for open models on agentic tasks. What about, like, general user perception?
That's strong too. On the LMSYS Arena leaderboard, where real humans blindly rate model outputs, Kimi K2 was ranked the #1 open source model and 5th overall around July 2025. So humans voting with their preferences seem to agree it's very capable.
Okay, so pulling back, what are the big implications here? What does Kimi K2 tell us about where AI development is heading?
I think it validates this whole complex approach. The combination of stable training for massive MOEs using things like QK-clip, plus this hybrid RL using verifiable rewards and self-critique against rubrics, that seems to be the blueprint now for building highly capable, open-source agentic models.
It's setting a new bar, a new methodology.
Absolutely. It shows how to tackle both the engineering stability and the agentic data scarcity problems together. It's not just a slightly better model, it's kind of a recipe for the next generation.
But no model is perfect. The paper was pretty upfront about limitations, right? What were the main hurdles they still face?
Yeah, they were commendably transparent. A key one is token over generation. Especially on really hard reasoning tasks, or if the tool instructions weren't perfectly clear, the model could sometimes generate way too much internal thinking text.
Like it gets lost in thought and runs out of space.
Kind of. It eats up the context window, the message gets truncated, and the final answer might be incomplete or just wrong. An expensive way to fail.
Did they try to fix that?
They worked on it during RL, adding penalties for being overly verbose, setting token budgets per task, but they acknowledge it's still an issue to watch out for.
What else?
They also found performance could sometimes drop if you enabled tool use when it wasn't actually needed. The model might default to trying a tool instead of just answering directly, which isn't always optimal.
Makes sense. And for that SW bench result, could it build a whole app from scratch in one go?
Not quite yet. They specifically mentioned that for large, complex software projects, just giving it a single huge prompt, one-shot prompting, didn't work very well. It still really benefits from an external agentic framework to help manage the steps and structure the process.
So it's a powerful component, but needs that scaffolding for really big tasks.
Yeah.
And finally, safety. What did they find there?
Generally robust, they said. But the safety tests did show some weaknesses, particularly against more sophisticated adversarial attacks. Things like iterative jailbreak or crescendo techniques designed to bypass safety filters had lower pass rates compared to simpler harmful prompts.
So core alignment seems decent, but there's still work needed on defending against tricky adversarial methods.
Exactly. As models get more capable, the safety and alignment challenges also get more complex. It's an ongoing arms race, in a way.
Okay, so wrapping up this deep dive,
Yeah.
Kimi K2 feels like a really significant milestone.
Definitely. It's this huge 1T parameter MOE, but it's the how that's key.
Yeah.
The stable mu-on-clip QK clip training, the hybrid RL tackling data scarcity with synthesis and self-critique. It's pushed open source agentic capabilities way forward.
And critically, the Kimi team didn't just publish the paper. They released the model weights.
Yeah, both the base model and the post-trained agentic version. They're basically giving the research community a very powerful, stable, agent-focused foundation to build on. That's huge.
So for you listening, this deep dive hopefully gives you that shortcut understanding. The cutting edge isn't just about size anymore. It's about these really clever engineering solutions like QK-clip for stability or hybrid RL for alignment that unlock these new agentic abilities.
It shows how intricate the process has become to push the state of the art.
Right, which leads us to our final provocative thought for you. The Kimi team put these advanced models out there specifically to accelerate research into agentic AI. Now that the whole world has access to these powerful open-source agentic foundations, what kind of new capabilities might emerge? What happens when the global research community starts plugging these things into, say, robotics or complex simulation environments or even financial systems?
Yeah, what complex real-world interactions are next on the horizon now that this level of open capability is available? It's going to be fascinating to watch.
It really is. Okay, thanks for joining us for this deep dive into Kimi K2.
See you next time.